First example we're going to look at here is proving a rectangle. There are three different ways to prove a rectangle, one of which is just the basic definition. If you have a quadrilateral with four right angles, you have a rectangle, something that's not new to us at this point. The second one may be a little bit new to us. If you have a parallelogram with at least one right angle, you have a rectangle. Now, sometimes people look at that and they say, wait a second, a quadrilateral with one right angle, that's not going to be a rectangle. What they're saying here is if you already know the shape is a parallelogram, then you just need an additional right angle to be able to show it's actually got to be a rectangle, okay? Why is that? Well, think about it. If you have a parallelogram, you know that opposite angles are congruent, okay? So for example, if it's already a parallelogram, you've got a right angle, you know the angle across from that angle also is going to be a right angle, all right? Parallelograms also have consecutive angles that are supplementary. So if that's a right angle, that's got to be a right angle to add up to 90 degrees, and then your opposite angles also are going to be congruent. That's going to give you four right angles, which takes you back to rule number one, okay? Now, some of you are thinking, well, how do I know it's not a square? Well, the big thing is we don't know anything about congruent sides. Maybe we have congruent sides, maybe we don't know, all right? The third one, a parallelogram with congruent diagonals. Once again, you can use a little bit of logic here. So if you have a parallelogram, opposite sides of a parallelogram are congruent, okay? I could draw diagonals in here, for example, and let's say that those two diagonals are congruent to each other. We know the opposite sides of those two triangles are congruent. And if we're looking at these two overlapping triangles, you've got a shared side there by the reflexive property, okay? So those overlapping triangles are congruent, and what that's going to tell you then is these triangles are congruent. We know these angles next to each other correspond. They've got to be congruent, but they've also got to be supplementary because they're angles of a parallelogram. So if they're going to be congruent and supplementary, that has to be a right angle, that has to be a right angle. Of course, if you have a parallelogram with any right angle in it, then you have a rectangle. It comes back to that rule. So if you can show a parallelogram has a right angle, if you can show a parallelogram has congruent diagonals, you know it has to be some kind of rectangle. Now, I could add on congruent sides or something and push it to a square category, but you know at a minimum that it fits into the rectangle category. The second example here is methods of proving a kite. One is the base definition. It's a quadrilateral with two disjoint pairs of consecutive sides congruent. In other words, if you break your quadrilateral into two halves, that's that disjoint pairs aspect of things. You're saying you've got consecutive sides congruent, and then in the other half, you've got another pair of sides that are consecutive and congruent, okay? Base definition, okay? By the way, there are lots of shapes that fall in that category. A square is technically a kite because it's got two congruent sides and two other congruent sides. It meets that definition, okay? It's also a square that has right angles, it's a square with congruent, or it's a kite with right angles and with congruent sides as well. Second definition here, it's a quadrilateral in which one diagonal is the perpendicular bisector of the other, okay? So if you draw a diagonal, and you draw a diagonal that's a perpendicular bisector, if you think back to the equidistance theorem says you've got a segment that's a perpendicular bisector of another segment. This point is on the perpendicular bisector, so it's going to be equidistant from the endpoints of that segment. This point here also is on the perpendicular bisector. It's equidistant from the endpoints of that segment, and that goes back to the original kite definition. Next, I'm going to look at methods of proving a rhombus. So if you want to prove a rhombus by definition is a quadrilateral with four congruent sides. All right, that's our basic definition. No surprises there. However, you can also say, if you can show it's a parallelogram, you can also just show that it's got a pair of consecutive sides congruent. So in other words, if I know it's a parallelogram already, and this side is congruent to that side, for example, think about what you know about sides of parallelograms. Opposite sides are congruent. So that side's congruent to that side's congruent to that side. That gives you four congruent sides. So just prove it's a parallelogram, use one of your 5 rules, get a pair of sides next to each other that are congruent, boom, you've got a rhombus, okay? The next one, a parallelogram in which either diagonal bisects opposite angles, all right? So parallelograms have congruent opposite angles. So you've got a shape here, you already know it's a parallelogram, you know the opposite angles are congruent. If you know that that diagonal bisects those angles, those are congruent angles, so you have two congruent angles that are both being bisected, which means these two halves are equal, those two halves are equal. Those are two congruent isosceles triangles, okay? Because we've got two congruent angles here, so that's going to give you two congruent sides, right? And we already know if you have a parallelogram with two congruent sides, then you have two consecutive sides congruent, then you're going to have a rhombus, okay? So the opposite sides are congruent, and you've got four congruent sides, your shape is a rhombus, all right? The last one. Not a parallelogram. You don't have to show it's a parallelogram for this last one. You just have to have a quadrilateral, four-sided shape with diagonals that are perpendicular bisectors of each other. Notice, it doesn't say the diagonals have to be congruent. They just have to be perpendicular, and they have to be bisecting each other. Maybe something that looks like this, okay? If you draw your shape around that, what you're going to find out is you get four congruent right triangles. Okay, if you look at the labelings there, they're all congruent by side angle side. If those are four congruent right triangles, all of those sides are congruent, you've got four congruent sides, you have a rhombus. Proving a square is super easy. You can just show it has four congruent sides and four right angles. Basic definition. With four right angles, it's a rectangle. With four congruent sides, it is a parallelogram. So, you can also just show that it's a quadrilateral, that's a rectangle, and not a rectangle and a square, a rectangle and a rhombus. If you can show those two things, you know you have a square. Finally, I've got a couple of simple rules for proving that a trapezoid is isosceles. First of all, basic definition, if the non-parallel sides of a trapezoid are congruent, you have an isosceles trapezoid. That's probably the most basic one. Also, if you can show that the upper base angles or the lower base angles of a trapezoid are congruent, you have an isosceles trapezoid. So maybe something kind of like that. That's enough information to say that your trapezoid is isosceles. Finally, if you can show that your trapezoid has congruent diagonals, so it's got to be a trapezoid, and if you can show that this diagonal is congruent to that diagonal, basically you'll end up with congruent overlapping triangles, and link back to that other definition. That is your last method for showing that you have an isosceles trapezoid.